Hi friends, see today I will be starting the 12th chapter in your second year physics, that is nuclei. Okay, today I will be starting the 12th chapter, that is nuclei. Right friends, so I am starting today the 12th chapter in your second year physics, that is nuclei. See, already I told you before, modern physics, that is dual nature, atoms and nuclei, all these together for around 5 to 6 marks in MSET. Okay, modern physics anta kalipi, dual nature, atoms and nuclei. Okay, so now I am starting the last one of this modern physics, that is nuclei chapter. So individually you can estimate around 1 mark or 2 marks from each chapter, but totally you will getting 5 to 6 marks in this chapter. Okay, now let us study about the nuclei. Already in before chapter we have studied about atom. I told you regarding atom, inside atom you will be having nucleus. Okay, inside you will be having nucleus, and in this nucleus you will be having protons and neutrons, and electron will be revolving and the centripetal force will be helping. So this you have studied regarding last chapter, 11th chapter. Now here in this 12th chapter nuclei, we will be studying about the mass of the atom. See how to define the mass of the atom and nucleus. See, nucleus means, you can see, this is the nucleus, there protons and neutrons are present. And for example, to define the mass of an atom, suppose this room, consider as an atom. Suppose consider this room as an atom. Inside this room, suppose if you take a small pin, aluminum pin, inside this room, if you take a small aluminum pin, that pin mass is the mass of an atom. So atomic mass, that means atom mass is so small, so it is completely inside the nucleus, so remaining portion completely vacant. So that is how you can define the mass of an atom. That means if you think this entire room as an atom, inside this room, suppose if you take a small pin, the mass of that pin is taken as the mass of the atom. So here what we will study is inside the nucleus, because we know the highest force in the universe is the nuclear force. It is around 10 to the power of 38. The same way electrostatic force 10 power 36. Gravitational force is almost least 1. So if you compare the ratio of different forces, gravitation is least, electrostatic 10 power 36, nuclear force is the highest force in the universe. That is why inside the nucleus the protons and whatever neutrons are completely bound together because of this largest force. ఎందుకంటే ఇక్కడ ఏం జరుగుతుంది, న్యూక్లియస్ లోపల, inside the nucleus you will be having protons, neutrons. Okay, you will be having protons and neutrons. Okay, so there will be force between proton and proton, same charge is repulsive force. Neutron and neutron, proton and neutron, neutron and proton. So like this, different forces will be there between same charges, repulsive. So proton and repulsive force ఉండవల్ల ఏమవుతుంది, the atom will try to become unstable, it will try to break up. Okay, so therefore, because this force is present inside the nuclear force, highest force in the universe, so atom inside the nucleus, the nucleons are bound, because actually between proton repulsive force is there, same charges, and neutron nuclear forces, proton neutron nuclear forces. So because of this force only it is existing. Okay, now we will try to find out a relation for the radius of the nucleus. We will try to find the relation for radius of the nucleus. So we know already in the alpha scatter experiment, Rutherford has done some experiments regarding different elements or different atoms. So from that what you have found is the volume, generally it is not spherical but nearly spherical. Volume of all the whatever atom element is taken as spherical. It is directly proportional to the mass number. See, we all know what is a mass number. Suppose if any atom is written like this, this is atomic number, this is mass number, and A minus Z is nothing but number of neutrons. Okay, A minus Z is number of neutrons, and atomic number plus neutrons, this entirely is called as nucleons, which is present inside the nucleus. Okay na? So according to him, the volume, that is 4/3 pi r cube, directly proportional to mass number, or if you take this side, 4 pi r cube proportional to 3a, or r cube proportional to 3a by 4 pi. Remove the proportional integer constant, 3a by 4 pi, taking 1/3 on both sides. Finally, r is equal to, this entire thing is constant, I will take it outside, k 3 4 pi power 1 by 3, a power 1 by 3. According to this one, finally, r, we got this constant, you can take it as r naught, and this one is a power 1 by 3. So the radius of the thing, okay, what you are deriving, radius of the nucleus, in other words, radius of the nucleus, or radius of the nucleus, we are finding out that radius relation is r naught into a power 1 by 3, and it is directly proportional to the mass number, directly proportional to the mass number, and this r naught is constant of proportionality, whose value is 1.2 into 10 to the power of minus 15 meters, or it is almost equal to 1.2 Fermis. Fermi is the scientist name, Fermi. Okay, so in general, because we can't take the unit, because nucleus is very small, you can't measure it in units of meters, so we will take another unit, that is called as Fermis, because 10 to the power of minus 15 meters or 10 to the power of minus 14 meters is equal to 1 Fermi. So this is the radius of the nucleus relation. So with this you can do so many problems. Okay, volume is directly proportional to the mass number, and thereby you got r is equal to r naught into a power 1 by 3. So this r is called as the radius of the nucleus, please. Okay, it's a very small value, constant value, that is 1.2 Fermis, or 1.2 into 10 to the power of minus 15 meters, and as we know, 10 power minus 15 is equal to 1 Fermi. Fermi is the unit, scientist name. Okay, so that is the radius. Okay, anta chinnadannamata value, radius value. Clear? Okay, so finally we got the nucleus radius value, that is 1.2 Fermis. Shall we go to the next one now? Right. Now we will try to define, because this subject is a modern physics, we are talking about atomic masses, we can't measure in kilograms or grams. Still further small unit you have to measure. That small unit is nothing but AMU. This AM is nothing but atomic mass unit. Okay, so hereafter in future we will be measuring the atomic masses in AMUs. One AMU can be defined as 1/12 of a neutral carbon atom. Carbon atom. So the exact definition of AMU is, atomic mass unit is 1/12 part of a neutral carbon atom. That means, you know from Avogadro number, this is mass number 12 grams is equal to Avogadro number 6.023 into 10 power 23 atoms, which is Avogadro number. Avogadro's number. Or from this one atom is in how much? 12 by 6.023 into 10 power 23. This is in grams. One atom is equal to unitary method, this thing. But what is saying 1 AMU 1/12 part of neutral carbon atom? That means into 1/12. So what is this value? You will be getting in grams. 1 by 6.023 10 power 23 grams. If you solve this value, you will be getting around 1.66 into 10 power minus 24 grams, and in kilograms 1 AMU value is given as, because we know 1000 grams is equal to 1 kg, or 1 gram is equal to 1 by 1000, which is equal to 10 power minus 3 kgs. Okay, so when you multiply with 10 power minus, you will get it as 1.66 or 1.67 10 to the power of minus 27 kilograms. So this is the factor value in kilograms. 1 AMU value anta one AMU atomic mass unit is equal to 1/12th of a neutral carbon atom, which is taken as 1.6 10 per minus 24 grams or minus 27 kgs. In future, you will be adopting this value for all numerical problems. Clear? Okay. So this is how we will define AMU, atomic mass unit. In future, this AMU value will be using in all numericals and other things. Clear? Right. Now, after finding out the radius of the nucleus as 1.2 Fermis, now let us go to the density. Second part, density of the nucleus. Density of the nucleus. So I told you just now, inside the nucleus protons are there and nuclear force is binding the protons and neutrons together not to break up because its force is very larger. Now density means what? What is the density? Density means mass per volume. So here mass means what? AMUs. Atomic mass AMU. By volume again 4/3 pi r cube. And that is A by 4/3 and pi ki vellipotundi 3 pi. And what is R? R is equal to R naught into A power 1/3. So substituting in the place of R, R naught into A power 1/3. Okay? R. Whole cube. చేస్తే ఫైనల్ ఇది ఎంత అవుతుంది? పైన ఏమో 3a కిందన 4 pi అండ్ హోల్ క్యూబ్ ఆర్ నాట్ హోల్ క్యూబ్ a పవర్ 1/3 హోల్ క్యూబ్ ఎంత అవుతుంది? కట్ అయిపోయి a మిగులుతుంది. అండ్ దిస్ ఈజ్ ఈక్వల్ టు డెన్సిటీ. అండ్ we know what is r naught value also. Just now I told you 1.2 into 10 to the power of minus 15 meters. When you substitute here, this value here, when you substitute that value here, a కట్ అయిపోతుంది, ఇంకా పైన ఏం లేదు. 3/4 pi, that means 3.14 or 20/7. When you substitute this value here, that is 1.2 into 10 power minus 15 whole cube, and you solve this one, you will be getting nearly around 2.2 into 10 to the power of 17 kg per meter cube. You can see how much high the value is, because all the things, protons and neutrons, are confined into the nucleus and nuclear force is binding. In some books they are giving 2.3 also, but actually 2.3 is for iron. Okay, generally the value varies from 2 to 2.2 generally. Okay, so generally the density of the nucleus is taken as 2.2 into 10 to the power of 17 kg per meter cube. Okay, clear? Right. Now let us go to the next one. Note down please. Clear? Right. Now after studying about the radius of the nucleus and density, let us go still further. Let us go still further. Okay. Now we will see what are isotopes. Okay. How many types are there? Isobars and isotones. Okay. So generally isotopes. Generally we can divide the following in this form: isotopes, isobars and isotones elements into. What are isotopes generally? For example, 1H1, 1H2 proton, hydrogen atom, deuteron, heavy hydrogen, or tritium. You can see same element, same atomic number, different mass number. Such an element is called as isotopes. So isotopes are the elements of same thing, not different elements, same elements. Same elements having same atomic number, different mass number. Okay, such an elements are called as isotopes. So you can take the example for hydrogen like that. Okay, in the same way coming to isobars. Isobars lo ఏమవుతుంది ఇక్కడ? Mass number will be same and atomic number will be different of different elements. Okay, of different elements. Okay, you can take the example for another also other than hydrogen. ఇంకా చాలా ఉన్నాయి. You can even take for oxygen. Oxygen you can take 8, 16, 17, 8, 16, 17 and also 18. This is stable one, these two are unstable. Okay, so oxygen 8, 16 stable one, 8, 17, 8, 18 are unstable nucleus. So you can take the example of oxygen atoms having same atomic number, same element, different mass numbers. Okay na? Isobars vachinappudu same mass number, different atomic number, but different elements andi. For example, you can take isobars carbon 612, nitrogen you can take carbon 612 originally, but unstable enti you can take 14. Unstable carbon you can take 14. The same as nitrogen, nitrogen 714 you can take. Nitrogen atom you can take 714. Here you can observe atoms of different elements. Atoms of different elements having same mass number, different atomic number. Here atoms of same elements, same atomic number, different mass number. Same mass number, different atomic number, atoms of different elements. These are isobars. Coming to isotones. Here what we'll see is different elements, atoms of different elements, different atomic number and different mass number, but same number of neutrons will be present. For example, you take lithium. You take lithium 3, 7, 3 atomic number, 7 mass number, and also you can take one more, beryllium. Beryllium 4, 9, I think 4, 8. Beryllium 4, 8. See here, in isotones, atoms of different elements, lithium 3 atomic number, 7 mass number, beryllium 4 atomic number, 8. Different atomic number, different mass number. Different elements, different atomic numbers, different. But if you minus A minus Z, 7 minus 3, 4 neutrons. Alage 8 minus 4, 4 neutrons. So, in such cases, those are called as isotones. Atoms of different elements, different atomic number, different mass number, but same number of neutrons, please. Clear? Right. Okay. So, this chapter you are carrying almost, I told you, all these three. They may give in this chapter 1 mark or 2 marks, or altogether modern physics. Dual nature atoms and nuclei will be getting 5 to 6 marks in MSET. Let us go to radioactivity. Next one is radioactivity. Radioactivity. Let us know what is meant by radioactivity. See, to understand this concept, you have to know the things of what is the protons and what is neutrons ratio. And a proton neutron or neutron proton ratio but activity and radioactivity you can understand whether the atom is stable or the nucleus is stable or unstable. Okay, na? So for that I will do one thing. Okay, I will explain one thing, that is regarding radioactivity. I will do one thing, otherwise before going into graph, this radioactivity అసలు రేడియోయాక్టివిటీ ఎందుకు అవుతుంది? Why it is causing unstability of the nucleus. Okay, radioactivity ఎలా కాజ్ అవుతుంది? This is due to what? Unstability of nucleus causes this radioactivity principle or property. And unstability అంటే ఏంటి? Again this comes N/P ratio. అంటే న్యూట్రాన్ ప్రోటాన్ రేషియో. Okay, so I'll explain with the graph very clearly. This N/P ratio itself tells about whether the nucleus is stable or unstable. While explaining the graph, I'll tell you. But who has invented this radioactivity? It was invented by Henry Becquerel. Accidentally. Henry Becquerel. Simply you can write as BQ. Okay, this was accidentally invented by a scientist called as Henry Becquerel. Okay, Henry Becquerel. Now, this one, you can understand one more point also regarding the radioactivity substances. Adentante, during this process, alpha, beta, gamma will be emitted. And alpha emission, beta emission, positive and negative beta, and gamma emission, electromagnetic waves. And during this radioactivity, what will happen is there will be alpha emission, beta emission, and also gamma emission, or you can also call the alpha decay, beta decay positive and negative, and gamma decay electromagnetic. Okay, and it is found from scientists. See, around there are 1500 known nuclei. According to the scientists, there are 1500 known nuclei, plural term. Nucleus means singular, nuclei means plural. Okay, so around known 1500 nuclei, around I think 260, less than 260 are stable. Less than 260 are stable nucleus. Okay, 260 are stable. Okay, and remaining, what happens is they will become stable by emitting alpha, beta and gamma decay. అర్థమవుతుందా? అంటే టు బికమ్ ఏ న్యూక్లియస్ స్టేబుల్గా ఉండడానికి కోసం అవి ఏం చేస్తున్నాయి? దే ఆర్ ఎమిటింగ్ ఆల్ఫా నెంబర్ ఆఫ్ టైమ్స్, alpha decay, beta decay means disintegration. Okay, and also gamma decay. By emitting these alpha, beta, gamma decays or disintegrations, they are trying to become unstable. Why they are unstable? Actually, I told you now, because of N by P ratio. So according to scientists, there are some 1500 known nuclei. Out of that, less than 260 are stable, it seems. Okay, out of that, less than 260 are stable. And remaining what ఏం చేస్తున్నాయి అంటే to become stable they are emitting alpha, beta and decay. Okay, now we'll later on I will explain regarding alpha, beta and decay, alpha, beta and gamma decays. But before that one, we'll do one thing. I'll explain the graph. Okay na? So already I told you, accidentally this radioactivity due to instability of the nucleus, Henry Becquerel was invented, and the year also, if you want, it is 1896. Around 1896 year. Okay, this Becquerel scientist has invented the radioactivity, that is accidentally. So before going into alpha, beta decay, let us see the stability graph. Very very important. ఇది కొంచెం అర్థం చేసుకోండి. Try to understand this one. This graph is called as a stability graph. Stability graph for neutron-proton ratio of the nucleus. Okay, so I'll try to explain very clearly. I'll take protons on the x-axis, protons values on the x-axis, number of protons. In the same fashion, neutrons on the y-axis, values. I'll take like this value 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, so on. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140. I'll take it on y-axis. These are neutrons, and these are protons on x-axis. So here, if you observe carefully, it is observed from scientists, atomic number less than equal to 20. Atomic number, the number of protons or electrons present inside an atom. Atomic number less than equal to 20, that is up to calcium. Starting from proton, hydrogen. Atomic number less than equal to 20. It was found, see here. It was found, this was the stability graph. For neutron and proton. This side is neutron and this side is proton. Stability graph, you can see it is a straight line. And for example, if you take neutron-proton ratio, it is almost equal to 1. For example, take hydrogen. How many protons are there? 1. Neutrons? 0. Okay na? Like 1 H2, deuteron, 1 proton, neutron 1. So N by P ratio 1 by 1, 1. In the same we can go for helium isotope, He24, 2 protons, 2 neutrons. So N by P 2 by 2, 1. So this N by P ratio is, suppose if it is equal to 1, then it is found that it is stable. For what? When Z is less than equal to 20. 20 elements. అర్థమవుతుందా? 20 వరకు అంటే అటామిక్ నెంబర్ 20 వరకు అంటే కాల్షియం 40 వరకు 20-40 వరకు. This is the stability graph. If more neutrons are there, atoms will be this side. If more protons will be there, it will be this side. Protons ఎక్కువైపోతే గ్రాఫ్ ఇటువైపు ఉంటుంది, న్యూట్రాన్స్ ఎక్కువైపోతే కొంచెం ఇటు సైడ్ ఉంటుంది. This is for atomic number less than equal to 20, please. Clear? If they are having more number of neutrons, slightly it will be away from this line. If more number of protons, slightly below this line. Atomic number less than equal to 20. Now for example, it was also found in this fashion also. And please make a note. Neutron, protons present inside the nucleus, I told you. Proton, 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 neutron, neutron, neutron. These all are charge dependent, please. Nuclear force is charge dependent. Same charge they will be having. Proton ki proton majna, proton, neutron, neutron, proton, proton means electrostatic force. Coulomb's repulsive force. Okay, na? And this proton, neutron, neutron, neutron is nuclear forces. So these are charge dependent nuclear force. Now let us study the second part. Second part, atomic number greater than 20. So atomic number greater than 20 చూసినట్టుగా అయితే ఇక్కడ న్యూట్రాన్ ప్రోటాన్ రేషియో less than equal to 1.6, greater than 1. Okay, greater than equal to 1 in the first case, atomic number less than equal to 20. Suppose if neutron proton ratio is less than equal to 1.6 or greater than equal to 1, atomic number greater than 20 అంటే vanadium ఇంకా మిగతా ఎలిమెంట్స్ ఉన్నాయి కదా అన్నమాట, like iron. Okay, you can take example. I'll write it here because no place. I'll rub these values. If neutron proton ratio is more than 20, I mean atomic number more than 20 అంటే NP, N by P is greater than 1, equal to 1, less than equal to 1 point. అంటే if you take iron 26, 56 ఎంత అయింది? Protons how many you are having? 26. How many neutrons? The 56 minus that is 30. So 30 by 26. Almost it is 1.5 to 1.6 neutron proton ratio. So like that if you take iron or any other examples you can take. Okay. These all again the stability graph little varies now. అంటే అర్థం ఏంటి ఇక్కడ చూడండి, ఇక 20 ఇది. See here. Up to 20. After 20 వరకు I told you, suppose if more of neutrons are there, little they will be going this side, more protons are there, they will be coming this side, N by P ratio. 20 తర్వాత atomic number తీసుకుంటే you will be getting the graph like this, stability belt. This is the graph. This is atomic number more than 20. So this is the stability graph. Stability graph. This is for Z is equal to 20, stability graph. So if more than 20 atomic number, the stability graph is like this. And if more neutrons are there, this is above, and less protons are there, I mean more neutrons ఉన్నప్పుడు పైకి, more protons ఉన్నప్పుడు కిందకి ఉంటుంది, N by P ratio. And ఇది కూడా ఎంతవరకు up to I think up to atomic number 83. Okay, up to atomic number 83, 209, 83, 209. This I think bismuth. 83, 209, that is bismuth I think. Okay, so up to 83, you can take this one. Last one, okay. Last one is 83. 83 atomic number and 209. This is, I think, bismuth in your periodic table. Bismuth. So that is the last atom there. Okay, na? So like that you can take and explain the stability graph. Clear? Any doubts regarding this one? So this all tells about the N by P ratio. Atomic number less than equal to 20 varaku, this is the stability graph. N by P ratio almost equal to 1. Suppose more neutrons, little will be going this side, more proton will be coming this side, up to 20. Atomic number greater than 20 ఏమవుతుందంటే N by P ratio కూడా కొంచెం మారుతుంది, but still they are stable. Still they are stable, like iron. Iron is the most stable one, 2656. So the graph goes like this, up to 83 atomic number, bismuth. So here also, if suppose more neutrons are there, it will go a little this side. If more protons are there, they will come this side. And like that, this N by P ratio is balanced, equal to almost 1.6. చూడండి కదా, N by P less than equal to 1.6, greater than equal to 1. So to become stable, ఏం చేయాలి? A nucleus, if it is unstable, to become stable, they are emitting alpha beta. So they have to adjust the neutron-proton ratio. If protons are there, less neutrons, some neutrons are added. If protons are less, okay, some more protons are added. And finally this neutron-proton ratio is balanced. And thereby, by emitting these alpha beta emissions and gamma emissions, decay, the nucleus try to become stable. Okay, so instability of the nucleus only mainly causing radioactivity, not stability. Okay, and why it is unstable? Mainly because of neutron-proton ratio. If neutron-proton ratio for atomic number equal to 20 up to, it is 1, and some nucleus, for example, greater than equal to 1, less than equal to around 1, now neutron-proton ratio less than equal to 1.6, greater than equal to 1, they are also still stable like iron. And after that again it becomes unstable. For uranium you can see, it is unstable. Uranium nuclei you can take 92, 235. So how many protons? 92. And what is neutrons? 235 minus 92. How many? 13 4. 143 are there. If you find the ratio, see, 143 by 92, it is more than that value. So that is why it is most unstable, and it is participating in nuclear fission reaction. Later on in the class I will be telling what is fission and fusion. Okay, so unstability of the nucleus only mainly cause the fission or fusion reactions. Clear? So understood this stability belt? Have you understood the stability belt? Any doubt? Right. Now I am rubbing this figure. Right. So this is how you have to understand the stability graph for stable and unstable nucleus. Okay. So all mainly depends upon the neutron-proton ratio. Up to 1.6 it is accepted. So after that value the nucleus becomes unstable and it is ready to participate in the nuclear fission reaction. Clear? So I am going to the next thing now. Alpha, beta and gamma decays. Okay? Right. Now let us try to understand what is alpha decay. Alpha decay or alpha emission. See, generally in the definition of alpha decay, we will define like this. Suppose this is parent nucleus, this is atomic number of parent nucleus, this is mass number. Now during alpha decay what happens? See here, a helium nuclei, alpha particle is nothing but helium nuclei. Alpha particle is nothing but helium nuclei is evolved. And in this case what happens is, the daughter nucleus, parent to daughter, what happens is, atomic number is reduced by 2 and mass number by 4 units. This is the main principle in the alpha decay. Alpha decay ఏం జరుగుతుంది? Parent నుంచి atomic number reduced by 2 units, mass number by 4 units. You can balance it 4, A minus 4, A minus 4 plus 4, A balanced. Again here 2 plus Z minus 2, Z balanced. So this is the expression for alpha decay. And make a note, either in alpha decay, beta decay also gamma may come out. Okay, gamma radiation may come out. Alpha lo ravochu, beta lo ravochu. It may come in any emission. So this is the basic concept in alpha decay. Parent nucleus nunchi 2 units is reduced from atomic number and 4 units in the mass number. Suppose if you want to give an example, take uranium 92, 235 or 236 you can take, or 238 isotope, you can take any one. Okay, you can take the example uranium isotope 92 238 తీసుకుందామా, 92 238. We will take 92 238 parent nuclei emitting alpha particle He24. So you have to balance here. ఇక్కడ ఏమవుతుంది, 2 units is reduced అంటే thorium 90 plus 92, ఇక్కడ 4 units reduced అంటే 234. So finally what you got? You got thorium atom. You got thorium atom. ఏమవుతుంది చూడండి, when it is emitting uranium isotope 238, alpha particle is coming 90 plus 2 92, 4 units is reduced, 234 plus 4 238. So thorium is coming outside. This is the alpha. Inka kavalante you can take some more examples also. Okay, you can take some more examples from a periodic table, but in the maximum we will be giving uranium 238 with thorium emission. Okay, any doubts? So this is how the alpha decay is done, please. Clear? I am dropping. Next I am going to beta decay. See, in beta decay we will be having two processes. Okay, positive and negative. Beta decay lo beta emission or decay will have positive and also negative. So beta and ఏంటి, fast moving electrons. So ఇక్కడ parent nuclei లో బీటా వచ్చినప్పుడు ఫాస్ట్ మూవింగ్ ఎలక్ట్రాన్స్ అంతే. బీటా అంటే E-1 0 ప్లస్ ఇక్కడ అటామిక్ నెంబర్ యాడెడ్ బై 1 యూనిట్ అండ్ మాస్ నెంబర్ రిమైన్స్ సేమ్. ఏదైతే ఇక్కడ డాటర్ న్యూక్లియస్ వచ్చిందో మాస్ నెంబర్, ఎందుకంటే A+0 A, ఇక్కడ Z+1 -1 Z. సో దిస్ ఈస్ ద డాటర్ న్యూక్లియర్ ఫార్మ్డ్. ఏమైంది ఇక్కడ, ఇన్ బీటా ఎమిషన్ యూ కెన్ సీ దిస్ ఈస్ నెగిటివ్ ఎమిషన్. beta negative emission, beta negative emission, fast moving electrons E-1 0 0 plus A -1 plus Z+1. So this is the parent nuclei in beta negative. దీనికి you can take for example carbon unstable 614 gives rise to E-1 0 plus ఇక్కడ -1 ఉంది, +1 యాడ్ అవ్వాలి అంటే ఏంటి, ఇక్కడ ఐ కెన్ టేక్ నైట్రోజన్ 7 14. సో యూ గాట్ నైట్రోజన్ atom or nucleus. సో ఏమైంది ఇక్కడ బీటా ఎమిషన్లో, దిస్ ఈస్ ఫాస్ట్ మూవింగ్ ఎలక్ట్రాన్ 7 -1 6. ఎందుకంటే ఇక్కడ ఏమైంది, అటామిక్ నెంబర్ ఇంక్రీజ్ బై 1 యూనిట్. అటామిక్ నెంబర్ ఈజ్ ఇంక్రీజ్ బై 1 యూనిట్. యూ కెన్ సీ Z+1. సో బ్యాలెన్స్ చేసుకోండి ఈక్వేషన్. ఇక్కడ ఇది -1 7 -1 6 14 + 0 14. సో లైక్ దట్ యూ కెన్ గివ్ ఎగ్జాంపుల్ ఫర్ కార్బన్ ఆల్సో. అదేవిధంగా యూ కెన్ గో ఫర్ పాజిటివ్ ఆల్సో. సి పాజిటివ్ కింద రాసేదా పాజిటివ్. సో ఇన్ పాజిటివ్ ఇఫ్ యూ అబ్జర్వ్ కేర్ఫుల్లీ, సి ఇన్ పాజిటివ్ decay a proton gives rise to E+1 0 plus N01. What happened, you can see 1 + 0 1 0 + 1 1. So it is giving an antiparticle of electron, positron with followed by neutron. So this can take as a positive beta decay. This is negative beta decay. So here a proton is giving rise to a positron, antiparticle of electron, and a neutron N01. Balancing equation 1 plus 0, 1, 0 plus 1. So like that you can explain for the positive decay of the beta. Okay. And sometimes you can frame the equation like this also. Please see, in beta decay, sometimes you can frame in this fashion: beta decay, positive decay. ఎలా అంటే neutron gives rise to proton, okay, proton, E -1 0, fast moving electron 0 1. ఇక్కడ you will be getting anti-neutrino. This is called as anti-neutrino. Elementary particles, ఇవన్నీ కూడా elementary particles. Okay na? So here negative beta decay is fast moving, negative beta decay, negative beta decay. That means neutron is coming out as proton, electron, anti-neutrino. You can see the balance 1 plus 0, 1, 0, neutron. Clear? You can take some more examples also if you want, okay, from your periodic table, and you can put the values there. Okay? Clear? Any doubt? Right. Coming to gamma decay, last one. Gamma can decay either in alpha emission and also in beta emission. Gamma is what? Electromagnetic wave. Okay? Gamma radiations are nothing but what? Electromagnetic wave. Travels with the speed of light. So during alpha emission or beta emission or beta decay, gamma can come out. Gamma can emit out. Okay? So gamma emission, electromagnetic waves, can come out during alpha decay or in beta decay. Okay, clear? Right. So are you following, all of you? See, this chapter is very concept based and also very interesting. And very interesting. Now let us go to our next one, radioactive decay law. Radioactive decay law. Now what is this law actually, radioactive decay law? Let us try to understand. అంటే ఇక్కడ ఏం చెప్తారంటే, for example, you are having some radioactive sample. This is x-axis, y-axis. Suppose you are having some sample, radioactive sample concentration. This is the concentration of radioactive sample. Let it be N0. Okay. Now, with respect to time, this sample, which is the initial sample, finally it is reducing. Finally it is reducing. We'll try to explain. Suppose the concentration, let us say initial was N0. This is the initial concentration or initial sample. Initial sample. Okay? Let us say this is the initial sample. Now what law says? Radioactive decay law. That means this whatever Dn means the sample, radioactive sample. This decay with respect to time is directly proportional to the sample. That means the amount of decay with respect to time, that is minus dn by dt, directly proportional to the sample value, concentration value, or minus dn by dt is equal to some k into n. N is the concentration of the sample. Or you can change this one as in this fashion: dn by n is equal to minus k dt. Now I will do integration. Now here what I will do, at time t is equal to 0, the sample was n0. At a time t is equal to t, let the sample is n. Are you following? At a time t is equal to 0, sample is n0, initial sample. concentration. At a time is equal to, let it be an integration of log x, 1 by x, log x, that is log n, limits n0, n, and here minus kt from 0 to t. So here if you apply the limits, log n minus log n0 with the base c, this constant k, I will put it as lambda. This is called as decay constant or disintegration constant So when you apply here minus lambda t or finally log n by log n0 with base c is equal to minus lambda t. This equation is called as logarithmic form. This is called as logarithmic form. This is the logarithmic form of radioactive decay law. That means the decay value, the dN by dt of the concentration is directly proportional to the initial value, sample. And finally, you got in a logarithmic form. So depending upon the questions, you have to use this formula or the next formula. This is logarithmic formula. N0 enti initial sample. And N0 is initial sample. N is undecay value. N is undecay sample. Initial sample. T is time. Lambda is decay constant. Are you following the point here? Any doubt? Okay? Right. I am rubbing the equation. Now same equation, write it in different form. This is logarithmic form. I will change that one into different form. E power minus lambda t, I can put it as n by n0. This is also called exponential form. N is equal to n0 into e power minus lambda t. This is exponential form. And this is logarithmic form. Okay? N is initial and n is undecay. N is undecay sample. Please copy this one. Any doubt? Right. Now, for example here, what I will do is, and one more point here, you have to understand. At t is equal to 0, if you put it here, what happens? You put it is t is equal to 0, e power 0, 1, then n is equal to n0. At t is equal to 0, n is equal to n0. At t is equal to infinity, then what happens? N is equal to n0 into e power minus infinity, that is equal to e power infinity. E power infinity means again infinity. 1 by infinity, again what happens? 0. Okay? So at infinity time, the sample may decays. Adavadna complete decays. Complete motto sample and the decay approach disintegration at infinity time. At t is equal to infinity, the sample motto sample will be decay. Okay? That may be 1 year, 2 years or 10 years or 40 years also it may take at infinite time. Clear? Right. Now same equation I will try to explain in different form. Same equation. For example here what I will do is, see, in the exponential form already I told you n is equal to n0 and e power minus lambda t. Let t is equal to 1 by lambda. So what happens now? N is equal to n0 and e power minus lambda. T and the 1 by lambda, lambda cancel in. N is equal to n0 and e power minus 1. That is equal to n0 by e. Or n is equal to 1 by e value. It is almost in the 0.368. 1 by e is 0.368 since the value from maths. So 0.368 of n0 and decay left over. Okay? లేదా 0.38 36.8% of initial sample. 36.8% of initial sample. This is another relation. ఇక్కడ గుర్తుపెట్టుకోండి, వాట్ ఈజ్ N here? Undecay sample. Capital N is undecay sample. So undecay ఎంత అయింది? N is equal to 36.8% of initial sample, undecay or leftover. 0.368 of N0 is equal to N, means this is undecay sample, not decayed, undecayed sample, radioactive element. Clear? So N is called as undecayed. And here already I given what is lambda. Lambda is called as decay or disintegration constant, please. So ఇందులోంచి T lambda ఫార్ములా ఏమవుతుంది? Lambda is 1 by T. T is time. So what are the units of lambda? Second inverse, minute inverse, days inverse, hours inverse, etc. etc. you can take. So the unit of decay constant is, because it is inverse of time, 1 by T, second inverse, minute inverse, hour inverse, day inverse, etc. etc. So that is the unit of decay constant, please. So please clearly understand, this N is undecayed sample, undecayed sample. Okay? And lambda is decay constant, please. Any doubt? Okay. We'll go further now. So these are some formulas regarding radioactive decay law. Now still we are, why this graph is left over is, this is for half-life period. I will try to explain half-life period now with that graph. Okay? The next one is half-life. Half-life period of sample. Okay? Half-life period of the sample. Now we will try to explain what is half-life period. And for example, let N0 is the initial sample of the radioactive element. Okay? Now what I will tell is, let the time required be to become half of the sample is T half, and the sample anta indi, N has become N0 by 2. To become half of the initial value, N is what? Undecay. To become half of the value, let the time be T half. Now put this one in your logarithmic form. Log N by N0 base E minus lambda T, or log N, what is undecay? N0 by 2 by N0 base E minus lambda T is becoming T half. So N0 cancel, this go to the top, 2 power minus 1, log 2 power minus 1 base E minus lambda T half, or minus 1 log 2 with base E minus lambda T half, minus minus gets cancelled. So finally, what is the formula I got? Log 2 with base E by lambda is equal to T half. This is the formula for half-life period of a sample. And we know log 2 with base E is 0.693 by lambda. So this is the formula for half-life period. And concentration is there, initial sample. So half, it has become half now in T half. Again next half, N0 by 2 by 2, 4. Next half, N0 by 4 by 2, 8. N0 by 16. N0 by 32, 64, 128, like that. So the values become half. Okay? So this is the formula for half-life period of a given sample. 0.693 by lambda, or log 2 with base E by lambda, where lambda is decay constant or disintegration constant, please. Any doubt? So you can apply the logarithmic formula and you can find out. Any doubts here? Very very important. And also you can give one more formula also for this one, that is number of nuclei left after n halves. Number of nuclei left after n halves. That means n half-life periods. For example, first enta initial sample, this is initial sample. Okay? Initial sample. For first half-life. sample and the undecay, n is equal to n by 2. Second half life, n0 by 2 by 2. Third half life, n0 by 4 by 2. అలాగే fourth, n0 by 8 by half. అలాగే nth half life ఎంత అవుతుంది? See this series, n0 by 2 power 1, n0 by 2 square, n0 by 2 cube, 4 to the 8 kada. If you see this series, n0 by 2 power n. Okay, so you will get the formula n is equal to n0 by 2 power n. Here n is number of half life periods. n అంటే ఇక్కడ ఏంటి? n is equal to number of half lives of a given sample. Any halves? 2 halves, 3 halves, 10 halves, or 100 halves. This n will tell you the number of half lives of a given sample, please. Clear? Any doubt? Okay, right. Now let us go further. This is how you have to explain the and understand the radioactive law and different formulas relating to that one. Okay, now let us go to the next one, that is activity of a radioactive substance. Next one is activity and a radioactive, not activity of a radioactive substance. Activity and a radioactivity and ఒకటేనండి. Activity of a radioactive substance. Generally, activity is given by R. Okay, activity is given by R. Please make a note. And the rate of decay already you know in the before one. Rate of decay of the sample is given by what? Directly proportional to minus dn by dt. And this already we know minus. అదే మైనస్ ఇక్కడ ఉంది కాబట్టి you can take minus this side, lambda into t. Lambda into t. అది lambda into n కదా. See what was the formula here? Minus dn by dt is equal to ఏంటి? డైరెక్ట్లీ కూడా n కదా. kn. Forgot? See, dn by dt rate proportional to n or minus dn by dt is equal to minus k into n. ఇక్కడ k అంటే ఏంటి? lambda into n కదా. సో minus dn by dt is equal to minus పోతుంది కదా ఇటు పక్క వస్తే. Already kept minus there, you need to put, and that k is what? lambda n. So this one you can understand now. Now minus dn by dt ఎంత అవుతుంది? lambda n. This one you can write as lambda into n. So rate of decay I can write in this fashion. R is equal to minus dn by dt. R is equal to, I can write as minus dn by dt, and of course this is equal to what? Lambda into n. Rate of decay is equal to minus dn by dt kada. So what happened? R here, R is equal to lambda into n activity, or already we know what is n here. N is equal to n0 into e power minus lambda t, or in before equation. So put it here, n0 into e power minus lambda t. Now at t is equal to 0 time, so what happened in this equation? Lambda n0 e power 0 again 1. So lambda into n0. But this lambda into n0 is what? Initial activity. So this one R is equal to, you can put here, R0 into e power minus lambda t. Same equation. N is equal to n0 into e power minus lambda t. R is equal to R0 into e power minus lambda t. So this is activity formula, and that is also same thing, same formula. Where there you use n. N is equal to n0 into e power minus lambda t in radioactivity. And activity you are using as R. Both are same. R0 into e power minus lambda t. Clear? Lambda is decay constant, I told you. The units are second inverse, inverse of time, day inverse, year inverse, etc. etc. Clear? Now we will try to write the units for activity or radioactivity. Units. Units for activity by radioactivity. See, generally, because of the scientist Henry Becquerel, because he is the scientist who invented this one accidentally, so on his name the unit is given. So 1 becquerel is taken as 1 disintegration per second or 1 decay per second. 1 becquerel is taken as 1 disintegration or decay per second. 1 becquerel is taken. This is the standard unit of activity or radioactivity. Okay, generally it is measured as becquerel. 1 becquerel is equal to 1 disintegration or 1 decay per second in generally. Or another unit, 1 Rutherford, another scientist, 1 Rutherford is taken as 10 power 6 disintegration per second or decay per second. 10 power 6 disintegration per second or decay per second. Disintegration or decay. And this is also again equal to 10 power 6 because 1 disintegration per second is equal to becquerel. So 10 power 6 becquerels. 1 becquerel is equal to unit for radioactivity or activity. 1 disintegration per second is equal to 1 becquerel. And 1 Rutherford is equal to 10 power 6 disintegration per second. Or that is equal to 10 power 6 becquerels. And we have one more unit, Madame Curie. Okay. So 1 Curie is nearly 3.7 in 10 power 10 disintegration per second. Okay. 10% disintegration per second. And this is equal to 3.7 10 power 10 again becquerels because 1 disintegration per second is equal to 1 becquerel. So these units they may come in the examination. Please make a note of that term. Okay. So Curie is also 1 unit. 1 Curie is equal to 3.7 in 10 power 10 becquerels or 3.7 in 10 power 10 disintegration per second. And 1 Rutherford 10 power 6 disintegration per second or 10 power 6 becquerels, and 1 becquerel is equal to 1 decay per second or disintegration per second. Clear? Right. Now let us go to the last part of this half-life, that is mean half-life. Let us study about what is mean half-life. See, generally mean half-life ante enti? See, mean half-life is indicated by tau. So this is nothing but average of all half-life. Average of all half-life periods. So therefore, mean half-life is given by 1 by lambda. Mean half-life tau ela rastaru definition? It is the average of all half-life periods. Average of all half-life. And 1 by, we already know what is 0.693 by lambda T half-life period. So 1 by lambda means 1 by 0.693 by T half. So T half will go to top. Tau is equal to T half paiki vellipotundi. T half by 0.693. This is nearly equal to 1.443. Nearly equal to 1.443 of T half. So what does it mean? Mean half is equal to 1.443 T half వచ్చిందంటే అర్థం ఏంటి? Mean half is greater than T half. That means mean half life is greater than half life period. You can see 1.443 times half. Okay, clear? So this is the definition of mean half life period. It is the average of all half life periods. So it is given by tau is equal to 1 by lambda or 1 by 0.693 by T half. And of course, tau is greater than half life period from the equation. Clear? Now let us go to Einstein's equation, next part, mass energy equivalence. Mass energy equivalence, that is Einstein's equation. Okay, na? Let us go to mass energy equivalence, Einstein's. Albert Einstein's mass energy, Einstein's mass energy equation, mass energy equation. So Albert Einstein already proved E is equal to mc square. So according to him, energy can be converted into mass, mass can be converted into energy. Okay? Or this equation also I can write in this fashion, delta m is equal to E by c square. Either E is equal to delta m into c square, or mass delta m is equal to E by c square. So I will explain this one, why I have written E by c square. So here what is happening according to Einstein, energy can be converted into mass or mass can be converted into energy. And of course total energy in the universe is constant. Here c means velocity of light. C is velocity of light, 3 into 10 power 8 meters per second. Now what is delta m here? That is called as mass defect, please. What is delta m? The delta m is called as mass defect. I will tell you why this mass defect has come up. Let us try to explain a small example. For example, this is a ball having some mass m at rest. Let us take a small example. A ball having some mass at rest. Now suppose this ball is in movement. Ball is moving. So when the ball is moving, okay, it is having some velocity. Now the question raises, which mass is more? Ball mass at rest or ball moving? Then we can say a moving ball. According to Einstein's equation, a moving ball mass is more than the rest ball. Why? Please see here. So what is the mass? Mass of a moving ball is how you will get it. When the ball is moving, it will be having kinetic energy. So according to this equation, what is the extra mass it is gaining? Generally, what is the formula? Mass of the ball at rest is given by E by c square. At rest. Mass of the ball at rest is E by c square. But when the ball is moving, what happens? Whatever this mass at rest, whatever mass at rest is there, mass at rest plus it will have extra mass. When the ball is moving, it will be having mass at rest, okay, plus extra mass. What is this extra mass? Because it is moving, it will be having kinetic energy. So if you apply this formula, kinetic energy by c square plus when the ball is moving, due to friction, heat energy is there by c square. This is the extra mass. So generally what happens, if you see the value c here, 3 into 10 power 8, 3 into 10 power 8 whole square in entandi, 9 into 10 power 16 in denominator. In the denominator you will having a huge value, means what happened to the final value? Neglected. That is why what we will do generally is, when any body is moving, in general according to Einstein, the mass is more than the rest mass. Because when it is moving, it is having kinetic energy and heat energy. Because this value is more, the value that mass is neglected. Clear? So this is how you can explain the Einstein's mass energy equation. That means energy can be converted into mass, mass can be converted into energy. So this one we will explain later on in mass defect clearly. Clear? Right. Now we will try to explain, after this mass energy equivalence of Einstein, what is mass defect? How we are get, why this mass defect is got? మనకి అసలు మాస్ డిఫెక్ట్ అనేది ఎందుకు వస్తుంది? ఓకే, వాట్ ఈస్ మాస్ డిఫెక్ట్? See, we all know nucleus ఉంది కదా. Inside the nucleus you are having protons, neutrons. And the nuclear force, highest force, is helping it to keep the protons and neutrons without breaking into two pieces or three pieces. So ఇక్కడ ఏం జరుగుతుంది? It was found that, for example, see how you will measure. See, this is an atom. Okay? And what are M and Z? Number of neutrons. So how the nucleus is formed? I mean nucleons. Protons plus neutrons. And this is mass of the protons. Z is atomic number. And mass of neutrons, A minus Z. Mass of neutrons. This is the nucleon's mass. Minus mass of a stable nucleus. This is equal to delta M and called as mass defect. So what it was found is the difference between the nucleon mass and a stable nucleus. This mass was greater than the stable nucleus mass. Okay? So it was found that the nucleon mass, okay, is greater. This mass is greater. This mass is greater than this mass. And why? What is happening? Because of the binding energy. What is binding energy? Binding energy and enti definition. Whatever Einstein has given, the same thing. Einstein equation enti? E is equal to mc square. M means mass defect. C is velocity of light. Please make a note here. Actually, this value you are getting in joules. ఎందుకంటే mass kilograms ఉంటుంది, ఇది velocity meters per second ఉంటుంది. You will get in joules. But energy will be calculating in million electron volts. Okay? So, దానికోసం you have a factor also, 931.5 into MeV. 931.5 into MeV. That is, binding energy can be got by delta M, mass defect, because it is in AMUs. So don't put it in joules. So to convert into million electron volts, mass defect into, if you multiply with this one, 931.5, you will get in million electron volts, binding energy. So what is binding energy? Let me have a small water, please. Let me have a small water. Now you can see here, just now I am telling about binding energy. అసలు binding energy అంటే ఏంటండి? See, whatever energy is required to form a nucleus, same energy is required to break the nucleus. That amount of energy is called as binding energy. And binding energy is nothing but E is equal to mass defect into square of the velocity of light. So it was found practically ఏమవుతుంది, when during breaking of the nucleus, some mass was escaped. ఎక్కడికి వెళ్ళిపోయింది ఆ మాస్? బికాజ్ ఐ టోల్డ్ యూ మాస్ అండ్ ఎనర్జీ. మాస్ కెన్ బి కన్వర్టెడ్ ఇంటు ఎనర్జీ, ఎనర్జీ కెన్ బి కన్వర్టెడ్ ఇంటు మాస్. సపోజ్ మాస్ ఈజ్ గాన్, ఎనర్జీ ఈజ్ గాన్. ఇఫ్ ఎనర్జీ ఈజ్ బికమింగ్ ఎస్కేపింగ్, మాస్ ఈజ్ ఆల్సో ఎస్కేపింగ్. దట్ ఈస్ వాట్ మాస్ ఎనర్జీ ఈక్వివలెన్స్ ఈక్వేషన్. సో డ్యూరింగ్ బ్రేకేజ్ ఏమవుతుంది, సమ్ అమౌంట్ ఆఫ్ మాస్ ఈజ్ ఎస్కేప్డ్ ఇన్ ద ఫార్మ్ ఆఫ్ ఎనర్జీ. సో దేర్ ఫోర్ దిస్ డిఫరెన్స్ వాస్ ఫౌండ్. Mass of the nucleus is greater than the mass of the nucleus, stable nucleus. This difference is called as mass defect. This difference is called as mass defect. So therefore, it is measured in AMUs. I told you before. So the standard value to calculate binding energy is equal to mass defect into, okay, a factor called as 931.5 million electron volt. This is got by this equation. This value will be getting in joules. Okay, and we also know 1 EV, 1.6 into 10 power minus 19 joules, and 1 MeV means 1.6 into 10 power minus 19 into 10 power 6. So 1.6 into 10 power minus 13. Like that you will get that value, substitute here, you will get this final value. This is the binding energy value of the final one. Clear? So like that we will be calculating the mass defect and binding energy in million electron volts, not in electron volts, please, million MeV. Clear? Okay. Now let me tell you a small graph regarding average binding energy. Let me give you a small graph regarding average binding energy. How to get average binding energy for different atoms or different nucleus, and from the graph what you can study, we'll see. Okay na? So జాగ్రత్త చూడండి ఇక్కడ average binding energy how will define average. See, average binding energy అంటే ఏమి లేదండి, binding energy divided by mass number. Mass number means per nucleon, ఒక proton ఒక neutron. What is average binding energy? Binding energy by mass number or average binding energy. Binding energy by enter for one proton and one neutron. For example, see this graph. If you observe the graph here for the periodic table atoms, okay, 1, 2, 3, 4, 5, 6, 7, starting from hydrogen, okay, and in the same way, average binding energy value 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 7.5, 6 and 8.8. Okay, and this one is for uranium 238 or 235, and this is for iron Fe26, 56. So if you observe carefully, the graph will be coming like this. So in this graph you observe, this is hydrogen atom on H1, and there we can go for lithium, so on and so forth. Lithium, carbon, okay. So for different elements, if you draw a graph and see the average binding energy, you can observe one thing. See the atomic number, and this is atomic number. This is atomic number Z, and this is average binding energy value Be by A. That means binding energy per nucleon, one proton and neutron in MeVs, please. And this is atomic number for different elements. Atomic number or mass number you can take, sorry, mass number. Okay, mass number, atomic number is because if you take element here, you will be having atomic number on the top, mass number, atomic number and mass number. You can write that also, mass number otherwise on x-axis. If you take like that, what it was observed is iron, you can see 2656, and the neutron proton ratio already explained, it is almost equal to 1.6. Stable atom. It was most stable atom. But coming to uranium 235 isotope or 238, when you divide with mass number, when you divide, మీకు అర్థమవుతుంది కదా, ఇక్కడ బైండింగ్ ఎనర్జీ ఎంత వస్తుందంటే 200 వస్తుంది MeV for uranium isotope. So 200 by, if you divide with 235 or 238, nearly you are getting 0.85 MeV. You are getting the binding energy value per in the nuclear fission reaction. Later on I will be telling. In nuclear fission reaction you are getting around 0.85 MeV. And not only that, you have seen the N by P ratio. N by P ratio చూసుకునే ఇక్కడ ఎంత ఉంది, protons అక్కడ neutrons చాలా ఎక్కువ ఉన్నాయి ఇక్కడ. You can see there in uranium 92, 235. How many neutrons are there? So many, you can see. 143 are there. So N by P ratio is very much larger than 1.6. 1.6 కన్నా ఎక్కువ. కానీ ఇక్కడ it is equal to 1.6. So it is more stable. And not only that, you can see the binding energy value for uranium is 7.6 MeV, and for this we will have around 8.8 MeV. Average binding energy value for iron is 8.8 million atom volts, and for uranium it is 7.6. It is having more value, average binding energy, than this one. And అంతేకాకుండా మీరు అబ్జర్వ్ చేయండి, as you go higher and higher, when the mass number increases, when the denominator value increases, the value decreases. మీకు అర్థమవుతుందా? As you go high and high in the periodic table. As the mass number increases, 235, 236, 238 isotopes, the value decreases. Thereby, the value decreases and అర్థం అవుతుంది ఏంటి ఇక్కడ, this MeV value, binding energy value also decreases. So it was found the most stable is iron. Okay, 8.8 MeV. So like this you can understand the average binding energy value. Clear? Now I told you just now, some nucleus are stable and some are unstable. Some nucleus are stable and some are unstable. And why that stability is there? You understood from stability graph. Because of neutron-proton ratio. And why the nucleus is emitting alpha beta to become stable. So because uranium isotope is unstable, it is subjected to nuclear fission reaction. It is subjected to nuclear fission reaction. That is uranium 92-235 when bombards with slow moving neutron, it goes to excited state 236 uranium excited, that is unstable, and it splits up into two nuclei, krypton, barium, okay, 36 56 plus 3 neutrons and use energy around 200 MeV. Barium 56, krypton 36 will be having. You can balance the equation. Barium 56, 140, krypton 91 if you take. Balance here 236 kada, 236 రావాలి మనకి 91. Suppose if you take 142, 91, 3 neutrons, 4, 5, 6, సరిపోయింది. Okay, I'll take 142. So barium 142, 56, krypton 36, 91 plus 3 neutrons and 200 MeV is released. So when a heavy nuclei like uranium 92, 235 or 238 bombards with a slow moving neutron, it splits up into two pieces, barium and krypton, and 3 neutrons are released. 3 neutrons for every fission. You can observe for every fission 3 neutrons. Again this one bombards, again 3 neutrons, again 3 neutrons, again this one bombards with uranium, again 3, and this one again 3. So here what happened? In first fission you got 3 neutrons, next how many you got again? 3, 3, 6, 9. Next you get how many? 27. So it is geometric progression, and this is called as uncontrolled chain reaction. What is this one? It is uncontrolled chain reaction. So you can see it is bombarding with the slow moving neutron. 3 neutrons. Again 3 gives rise to what? Again participating this and this. 3, 3, 6, 9. Again these give to 27. Like that it is a geometric progression, and it is uncontrolled chain reaction. Same thing happens in the atom bomb. And you can also observe an example in Nagasaki and Hiroshima. It's a plutonium bomb in 1945, something like that. Okay, so because of that bombing, every crop has failed there till today. Now the crops are coming there. So that much of radiation effect will be there in atom bomb. Okay, in atom bomb. So atom bomb principle is nothing but nuclear fission. It is uncontrolled chain reaction. So what is controlling here then? That controlling is nothing but nuclear reactor. Okay, so in nuclear reactor this control process will be there, please. Em chestaru? Nuclear reactor loni you have so many nuclear reactors in Baba Atomic Research Center. Baba Atomic Research Center lo we are having a nuclear reactor called as Apsara. Name as Apsara nuclear reactor. And nuclear reactors can be used as two processes for two ways. One is for peaceful One is for peaceful, ingoti for disaster. Peaceful means to generate electricity. To generate electricity. Disaster for making bombs, atom bombs. So you can manchiki use cheyochu, chediki use cheyochu. Nuclear reactor to generate electricity and to make bombing also, because uncontrolled chain reaction will be there. Clear? Now the main thing in nuclear reactor is the following things will be there. Nuclear reactor lo examination adugutunnadevi. In nuclear reactor the following items will be there. First one is fuel elements like uranium isotopes 92, 235 or 238 isotopes are used. These are the fuel elements. Second one, you'll be using as a moderators. Moderator ఉంటుంది. Moderator. Generally moderator function ఏంటంటే it will slow down the fast moving neutrons to thermal neutrons. It will fast moving neutrons are reduced to thermal neutrons. Thermal neutrons. Speed ga velle neutrons ki it is changing into converting into thermal neutrons. Moderator main function ente it slow downs the fast moving neutrons to thermal neutrons. Mainly ఏంటంటే water. Normal water is used as a moderator in nuclear reactor. Sometimes deuterium, heavy water, deuterium, heavy water is also used, and of course graphite is also sometimes used, graphite. Okay na? So these are the fuel elements. Uranium 238 isotopes are used in nuclear reactors. Moderator ఏంటంటే it reduces the speed of the neutrons to thermal neutrons like ordinary water, heavy water, deuterium and graphite. And next one is, just I told you Apsara nuclear reactor in Baba Atomic Research Center. In Apsara nuclear reactor, the moderator is nothing but water. In Apsara reactor, the moderator is used as ordinary water is used as the speed control of the neutrons to thermal neutrons. Apsara nuclear reactor. Now coming to the coolant. Third point, coolants. Coolants పని ఏంటి న్యూక్లియర్ రియాక్టర్లో? జనరల్గా కూలెంట్ ఏం చేస్తుంది? ఇట్ అబ్జార్బ్స్ హీట్ ఎనర్జీ. Heat is absorbed in the nuclear reactor. Okay? And finally what happens? It sends this heat to the boiler. అదవుతుందా? కూలెంట్స్ పని ఏంటంటే it absorbs the heat energy released in the nuclear fission reaction. Okay, it absorbs and that heat is sent to the boiler to heat water. This heat is sent to the boiler to again heat the water. That is the main function of the coolants. And the coolants ఏం వాడతారు జనరల్గా? Again water, air, liquid sodium, air, ordinary water is also used as a coolant, H2O, okay, carbon dioxide, CO2, air, and liquid sodium is also used as a coolant. Okay, and these should have high specific heat capacity. These should have high specific heat capacity. These should have a high specific heat capacity. అర్థమవుతుందా? So that is the main function of the coolant. Next one is control rods. See, in the nuclear reactor, control rods also plays a main role. Control rods పని ఏంటి? నాలుగోది control rods ఏంటంటే cadmium, boron. These rods they'll introduce inside the reactor, and the main function is the speed is reduced. Okay, that means it reduces the rate of fission. Rate of fission is reduced. That means the K value is balanced. K value is balanced to 1 nearly. K value is balanced to 1 and A. So cadmium and boron rods are introduced, and it absorbs the excess neutrons released in the fission reaction. And the K value, reproduction factor, reproduction factor K, reproduction factor K value is maintained as 1. Okay, and this K also you can define like this. Suppose if K is equal to 1. Now what is K? First of all, let me define. K and enti? Number of fissions in present generation, by number of fissions in previous generation, by number of fissions in previous generation. K ni ఎలా డిఫైన్ చేయొచ్చు reproduction factor ni number of fissions in present generation by number of fissions in previous generation. Number of fissions in in previous generation. Present generation లో ఎన్నైతే fissions అయ్యాయో 1 2 3 divided by number of fissions in previous generation, that means before. Now suppose if K value is equal to 1, just now I told you the control rods, it absorbs the excess neutrons and balance the K value equal to 1. That means present generation is equal to previous generation fissions. So if K is equal to 1, what happens here? One fission causes one fission. One nuclear fission causes only one fission. Because K is equal to 1, absorbs the excess neutrons. So one fission causes only one fission. So here rate of energy is constant. Here rate of energy is constant. Not increasing or decreasing, constant will be there, rate of energy. Okay? Rate of energy is constant here. So one fission causes one fission. Suppose if K value happens to be greater than 1. If K value is greater than 1, ఏమవుతుంది? One fission causes more than 1. One fission causes more than one fission. That is more than one nuclear fission. One fission can cause more than one fission. అంటే more than one nuclear fission. 2 fissions అవ్వచ్చు, 3 fissions అవ్వచ్చు. If K is greater than 1, అంటే number of fissions in present generation divided by number of fissions in previous. And in this case K is greater కాబట్టి rate of energy liberated increases. Rate of energy liberated increases, please. Rate of energy liberated ఏమవుతుంది? Increase అవుతుంది. Okay? Rate of energy increases, please. Understood? Now next one and last one. If K is less than 1, third one. If K is less than 1, number of fissions are in decreasing order. If K is less than 1, ఏమవుతుంది? Number of fissions are in decreasing. Number of fissions are decreasing and rate of energy also decreasing. Rate of energy is also decreasing. అదవుతుందా? If K reproduction factor is less than 1, equal to 1, present generation, previous generation, number of fissions is same. If K is greater than 1, one fission may cause more than one fission, nuclear fission, and rate of energy liberated increasing. Here rate of energy will be decreasing when K is less than 1. When K is less than 1. And number of fissions will be decreasing. So this is the story about the nuclear fission and reactions. And last one I have left over, containment. అంటే during the nuclear fission reaction, so much radiations will be coming out, and that may cause very effect to the person staying around that nuclear reactor. So containment ఉంటుంది అన్నమాట. Containment of thick wall. Containment. That means a thick wall is constructed. Thick wall of concrete. Around 1 meter thickness and 100 centimeters. So this much thick wall is constructed around the nuclear reactor such that the radiations may not come outside and may affect the people living there. So this is called as containment wall. Okay? Containment. And ఒక ప్రొటెక్షన్ వాల్ లాగా ఉంటుంది ఇది. అది ఎంత అండి థిక్ 1 meter థిక్నెస్ కాంక్రీట్ అనమాట. సో దట్ the radiations will not come outside and affect the people living outside there near the reactor. And last and final one left out, that is nuclear fusion, please. Nuclear fusion, and this will be the end of the chapter now. Last one, nuclear fusion. See, nuclear fusion is very easy. Two lighter nuclei like proton and proton gives rise to a heavier nuclei like deuteron plus some energy. Two lighter nuclei, proton, proton, hydrogen. In the same way again, deuteron and again proton gives rise to helium isotope. Some energy may come out. Helium isotope. This is helium isotope. This is deuteron. Again this helium isotope again reacts with proton, gives rise to He2 4 alpha particle plus a positron plus some energy. This is antiparticle of electron, positron. See the balancing equation, 2 plus 1 3, 4 plus 0 4, 2 plus 1 3, 3 plus 1 4. These three are called as proton-proton cycle. Proton-proton cycle. These three equations are called as proton-proton cycle. This entire three can be represented as a single equation like this. 4 times proton hydrogen gives rise to He2 4 plus E plus 1 0 positron plus 24 MeV millielectron energy. ఒకసారి బ్యాలెన్స్ చేద్దాం ఈక్వేషన్. 2 times. See, 2 plus 2 4, 4 plus 0 4 4. So this equation is balanced. This is the single equation for all these three proton-proton cycle. Instead of writing all these three proton-proton cycle, you can express this single equation. Now observe carefully, in nuclear fusion, what was the energy released? 200 MeV. In nuclear fusion, in atom bomb, and this is hydrogen bomb example. This is example of hydrogen bomb. Here the energy release is 24. So we will compare with atom bomb and hydrogen bomb. What is the average binding energy in this one? 200 by 235. That is 0.85 MeV. What about here? 24 MeV by 4. 6 MeV. So which is more dangerous? Nuclear fusion is more dangerous than fission. That is why hydrogen bomb is more dangerous than atom. You can observe here. Almost it is 6 to 7 times. So hydrogen bomb, that is energy of sun and stars, continuously how they are getting from lakhs of years. కొన్ని లక్షల సంవత్సరాల నుంచి ఎనర్జీ ఆఫ్ సన్ అండ్ స్టార్స్ ఎక్కడి నుంచి వస్తుంది? దే గెట్ ద ఎనర్జీ ఫ్రమ్ ఐదర్ ప్రోటాన్ ప్రోటాన్ సైకిల్ ఆర్ కార్బన్ నైట్రోజన్ సైకిల్. దీని ద్వారా లేదా కార్బన్ నైట్రోజన్ సైకిల్. కార్బన్ నైట్రోజన్ ఏ లేదండి, కెమికల్ రియాక్షన్స్ C12 C612 plus hydrogen. Again the equations are there, 6 to 7 equations. అర్థమవుతుంది మీకు పాయింట్? సో from lakhs of years the energy of sun and stars are getting from either they may get from carbon nitrogen cycle or from proton proton cycle. Clear? So here you can observe very clearly hydrogen bomb, whatever energy is present in the sun and stars, you can see for fusion, ఒక ఫ్యూజన్ కి యావరేజ్ బైండింగ్ ఎంత అవుతుంది? 24 by 4, 6 MeV. This is for average binding. For nuclear fission ఎంత వచ్చింది? 200 by 235, 0.85. So fusion is 6 to 7 times greater than fission reaction. Clear? Therefore hydrogen bomb is more dangerous than atom bomb. This is how you can differentiate between the nuclear fission and nuclear fusion reaction. Clear? So this is the end of the chapter for nuclear, and I have taken as nucleus in one shot. Okay? Again we'll be meeting in the last chapter. Please study well. Okay?